Now let's see what Stoke's theorem in vector calculus tells us. Stoke's theorem is about the circulation of a vector field. Let's say we have a vector field like this and we want to find out its circulation around this mathematical loop. Now this circulation is defined as the line integral of the tangential component of the vector field E around this loop gamma. Let's say at some point on this loop here we have this vector field E pointing in this direction and an infinitesimal length vector dl is pointing in this direction. Then the tangential portion of this vector field E along this infinitesimal length would be this. And if we take the line integral of this ET around this whole loop, it will be called the circulation of vector field E around this loop lambda. We can actually rewrite this thing as a line integral of the dot product of vector field E. Now what happens if we divide the loop lambda into two contiguous loops, lambda 1 and lambda 2? That is, if this is the loop lambda, then this is lambda 1 and this is lambda 2. Then the total circulation of the vector field E around this whole loop will be equal to the circulation in the loop lambda 1 plus the circulation in the loop lambda 2. But you may ask, how can these two circulations give us the total circulation, as we have to use this extra path twice? But this extra path will not affect us because the circulations here for the two loops are in different directions, as you can see. So these two circulations will cancel out each other. And that's how we get the total circulation to be equal to the circulation in these two contiguous loops. Now what if we divide this loop into a large number of contiguous loops like this? Well, then the circulation of vector field around that loop will be equal to the sum of circulations around all the small loops. But notice one thing, we have considered that these small loops are in the same plane of the larger loop, but it doesn't actually have to be like that way. Actually, the small loops can lie on any surface having lambda as its boundary, like this case in the figure. And we can actually consider the loops to be small enough so that they can be considered as flat rectangular loops, like in this case. Now let's find out the circulation around a rectangular loop from a different point of view. And let's choose a coordinate system in such a way that this rectangular loop lies in the xy plane. Now let's say a vector field E is passing through the loop like this. So if we zoom into this small rectangular loop, it will look something like this. Let's say this dimension of the small loop is delta x and this is delta y. The coordinate of this point is x, y, and the vector field E is passing through it like this. Now we can actually divide the circulation of this vector field E around this small loop into 4 segments: 1, 2, 3, and 4. So the total circulation around the loop is the sum of the segments 1, 2, 3, and 4. So the line integral of this vector field E here in the segment 1 will be the component of the vector field E along this line at this point, which we will call EX1, times the length of the segment, which is delta x. And for the second segment, it will be component of E in this direction at this point, which we will denote as EY2 times the length of this dimension, which is delta y. Similarly, we can find out the circulations in these two segments as well. But the sign of circulations for these two segments will be different from these two segments, because for segment 1 and 2 the direction of circulation is anti-clockwise, and for section 3 and 4 it is clockwise. So the total circulation would be the algebraic sum of circulations for all 4 segments. Now, to get an insight about this result, let us consider these two parts separately. Let us consider this portion first, and if we take delta y common, we'll have EY2 minus EY4. Well, what is this thing? This is just the change of y component of the vector field E when we go from point 2 to point 4, which we can write down as rate of change of the y component of the vector field E with respect to x times this small dimension delta x. Similarly, we can find out EX3 minus EX1, that is the change of component of the vector field E from point 3 to point 1, to be the rate of change of EX in this direction times the distance between 3 and 1, which is delta y. So if we put these values into this equation and take delta x times delta y common, we'll have this term, the rate of change of EY with respect to x minus the rate of change of EX with respect to y. And if you see it closely, you will notice that this is just the z component of the curl of vector field E. Now, if you want to write this in a coordinate independent way, then it will be the component of the curl of vector field E perpendicular to this surface area. So let us denote that direction with n. Then we can find the component of the curl of vector field E in the direction n by this dot product with the unit normal n hat. And remember that we can write this thing as the area vector dA. So this becomes the expression for circulation of a vector field E around a small rectangular loop. Now, how do we extend this result to multi-connected loops where the area of the loops are very, very small and the number of the loops tend to infinity? Well, you guessed it right. We have to integrate this quantity over that whole surface. This is that surface integral, and this is what we call Stoke's theorem.